Hey, ladies and gentlemen, let's get started with 1.1. I'm going to split the video in two parts because I think if I do it together, it's going to be pretty long. So here we begin. This is the same as what I did in class. If you were absent or just want to look at it again, our unit 1 is referred to as the piecewise and power function. We do briefly mention about power function in today's lesson. I'll keep switching the colors, so just bear with me. Five topics covered today are going to be intercepts, symmetry, even odd, power functions, and operations. Now, intercepts. You've done intercepts for a very long time. Intercepts basically are x and y intercepts together for two intercepts. And I have been given this equation. The idea is that we do not have a calculator accessible to us. Without the calculator, we're trying to find the x and y intercepts of this equation. Now, with x-intercepts, we all know it's a fact that y-coordinate is 0, and with y-intercepts, we all know that x-coordinate is 0. So I'm going to use that piece of information in the equation to go ahead and try and find the x and y-intercepts. Plug in 0 for y, that gives me 9x squared equals 36, x squared equals 4, and x equals 2. A lot of us sometimes miss the fact that square root of 4 is 2 and negative 2. So I was trying to find an x-intercept. I ended up finding two x-intercepts. Trying to find y-intercept, same thing, take the original equation, plug in 0 for x instead. So all I end up with is this, and y equals 9. So I did find one y-intercept, which is 0, 9. And these three will be my answers for all the intercepts. Literally, that was topic number 1, how to find intercepts algebraically. This is definitely not the first time you're looking at it, so I'm going to move on to topic number 2. Topic 2 is in detail talking about symmetry of graphs with respect to the x-axis, y-axis, or the origin. Now, when we talk about symmetry, you want to keep two things in mind. The visual aspect of symmetry, which means when the graph is provided to us and we look at it and identify what kind of symmetry it has, and then algebraic part, which assumes that we do not have access to graph or any graphing tool, and we got to be able to algebraically figure out if a graph is symmetric with respect to x-axis, y-axis, or the origin. Another thing, just a quick reminder, when a graph is symmetric with respect to x-axis, y-axis, we call them even functions, even functions. When a graph is symmetric with respect to the origin, we call them odd functions. When a graph is symmetric with respect to x-axis, those are not functions. They're actually not functions, and hence they are not classified as anything. Because x-axis symmetry, here's an example of x-axis symmetry. This graph is symmetric with respect to x-axis, but it fails the vertical line test, and hence is not a function. So keep this in mind. Let's go ahead and get started. Here's the first example. I have a graph in front of me. This graph clearly has x-axis symmetry, which means what I see above the x-axis, I see the same thing below the x-axis, perfect reflection. Now with x-axis, please keep the algebra part in mind. For every point x comma y, there has to be a point x comma negative y in the graph, on the graph. For example, if this point here is, let's say, 5 comma 4, then there has to be a point down here which will be 5 comma negative 4, and hence the generic form, which is xy and x negative y, which means, again, if you notice carefully, x really hasn't changed, but y swapped sign. Keep that in mind because we're going to use it briefly. X does not change, y swaps the sign. All right, coming to the next one, which is symmetry with respect to y-axis, clearly you can see that the blue and the pink are reflections of each other over y-axis, and hence this graph has axis symmetry with respect to y-axis. Algebraically, it means that for any point x comma y, there has to be a point negative x comma y, which means if this is a point refers to as 5 comma 3, then automatically there's going to be a reflection of that point, which will be negative x comma y. This is also a function, so I can go ahead and write the function notation to it, which means f of x will, if f of x equals y, then f of negative x will also equal y, because x can be interchanged with negative x, but the function is back to the original function. Another way to give this piece of information, is f of negative x, you could also rewrite this as f of x, because y and f of x are the same thing. So what you want to take away from this slide is the fact that this is the visual aspect of it. Where's my, this one? Yeah, I like this tool. So this is the visual aspect of axis symmetry with respect to y-axis. This is algebraic representation of the same concept, and this right here is the function notation of this exact same concept. Keep in mind, when x is replaced with negative x, a graph that's symmetric to y-axis will end up being the original function again. And I'll show you examples for sure. Third one, obviously, is symmetry with respect to the origin right here. So what you see in the first quadrant, you're going to see a reflection of it in the third quadrant, and vice versa. If you see any part of the graph here in the second quadrant, you're going to see a reflection of it in the fourth quadrant. Like, for example, if I have something like that here, then I would also see something like that on this side of the graph. So that's the visual representation. Let's do the algebraic representation. All that means is for every x comma y, there has to be a negative x comma negative y on the graph. This would be in the first quadrant, and this would automatically be in the second quadrant. If there is a point in the second quadrant, negative x comma y, then there has to be an x comma negative y. Also, which, if this is in the second quadrant, this will be in the fourth quadrant. Okay, in function notation, please write that when negative x is plugged in as the input, the output will be opposite of the original function. Not the exact same function, but opposite of the original function. Keep that in mind. And of course, when we do examples, hopefully we'll be able to connect better. I do have a little math Excel question. I think I put this on homework 1.1 today. This one's saying if the graph of an equation is symmetric with respect to the origin. So it's already told me this is symmetric with respect to the origin. And 3 comma negative 4 is a point on the graph. Then what else will also be a point on the graph? Keep in mind this is origin symmetry. If you visualize 3 comma negative 4, that has to be a point here in the fourth quadrant. If this is symmetric with respect to the origin, then there has to be a reflection of that point in the second quadrant. And in the second quadrant, x is negative and y is positive. So if you plug that in, it should work. Hope that makes sense so far. I am going to move on. This slide provides you all three of them at the same time. Let's not forget about one more visual concept. This is y-axis symmetry, the second one. Such functions are called even functions, although I just mentioned it before. This is origin symmetry, O for origin, O for odd. These aren't even functions, so we do not classify them. There's some more practice problems here. This kind of lists the same thing. One more time, this is odd function, this is even function, and this is neither. All right. More practice ones. This is neither, this is odd, that's even, this is neither, odd, odd. Yeah, that's it. Take your time, pause the video, try and answer them yourself first, then move on. Alrighty, this is an example from Math Excel, but I will move on. I did discuss this in class. Here's the main example. This one's saying test for symmetry. And I have clearly been given an equation, and I need to test it for symmetry. Now, keep in mind, we are assuming we do not have access to any graphing tools. And I need to yet be able to figure out if this graph is symmetric with respect to anything or not. So what I'll do here is, I'm going to start with the y-axis concept. And what I just wrote previously, you've got to tell yourself that if a graph is symmetric to y-axis, then f of negative x will equal f of x, which means whatever the original function is, keep in mind this y can simply be replaced with f of x. It's just a fancy way to write functions. When negative x is plugged in as input and the function is evaluated, if we end up with the original function, we can comfortably say that we have a function that's symmetric to y-axis. Let me show you what that means. So in the function, I am going to replace x with negative x minus 9 over x squared plus 2. Plug in a negative x here, plug in a negative x here. And let's evaluate it. Please know that negative x whole squared is back to being x squared in both situations, in the numerator and denominator. Now notice this is the same as our original function. So when we substituted negative x for input, we got the original function back. I was like, oh, okay, this is back to being f of x. Oh, that's not going to stay. This is back to being f of x. So what I wrote down here, this part is actually true, which means I can comfortably say that this graph will have y-axis symmetry, which means it will be symmetric around y-axis. I can comfortably say that. Now look at the next one. To be able to figure out origin symmetry, you really don't have to do anything extra. The idea here is if a negative x is plugged in for the input and you end up getting negative of the original function, then we declare that the function has origin symmetry. But you know what? We just did all that work. We already just plugged in negative x for input. What we got was not negative of f of x. In fact, we got f of x. So this part isn't true because we just did the math. So there's no point of doing the math again. So this one does not have any origin symmetry. I can say that. I hope that makes sense. Um, I'll do one more example and show you what origin symmetry will look like. And the last one I'm going to do is the x-axis symmetry, which if you notice, let's go back to the x-axis symmetry. What we do, right? In x-axis symmetry, there's a little lag on the iPad. I'm sorry about that. And I don't know, I'm trying to make it go upwards, but it's really not going as fast as I would like for it to be. Here's x-axis symmetry. Notice that in x-axis symmetry, x doesn't even change. So I'm not going to plug in negative x as an input. The only thing that changes is y. So I'm going to plug in negative y for y and see if I get the same function or not. Here it is. So instead of y, I'm going to plug in negative y. And nothing else is y, so the right side of the function stays the same. And when I do that, I notice, look at this, what I got, and look at the original black one. These two are not the same. These are not the same. Because 5 is not the same as negative 5. They're opposites of each other. So I did not get the original function back. I'm going to say no x-axis symmetry. So we figured out without really graphing this function that this function will have y-axis symmetry. It's going to be an even function. I can say that for sure. But what I did was I did graph it actually just to show you it. This is the graph of the function. You can clearly see it does have y-axis symmetry. It doesn't have any of the other ones. Let me show you another example on the exact same topic. I do have 5 problems in front of me, A, B, C, D, E. Let's pick any one of them and work on it. And I do know that C is a good example to work on. F of x equals x to the third power plus x. And I want to identify if it's even, odd, or neither. Even, odd, or neither. Which means, does it have a y-axis symmetry? Does it have x-axis, not x, origin symmetry? And if it doesn't have any of them, we're going to classify it as neither. And it's the exact same first step. What you want to do is, instead of x, plug in negative x to the third plus x. Let's plug in negative x, plug in negative x. Let's see what we get. Negative to the third power, negative will stay, and then minus x. So when I plugged in f of negative x, did I get the original function back? These are not the same. I did not get the same function back, which means this graph is not even. It does not have y-axis symmetry. Now let me undistribute the negative. I hope you remember what undistributing was. When I do that, notice that what I get is negative of the original function, negative of f(x). And this is the criteria for origin symmetry. Origin symmetry. And because it does have origin symmetry, I'm going to classify this as odd function. Hope that makes sense. So those are the 2 examples I have for even, odd, or neither type of category. All right. Of course, there are more examples here, A, B, D, E. I'm not going to do those in the video, but I do have them worked out in the following slide, and you can try them on and check for the answers. Alrighty. Actually, power function. I'm going to stop the video here because this is topic number 4, which was power function, and then I have operations of functions. I'm going to cover that in the next video, so stay tuned.